Hi, folks. Today we're going to talk about non-Euclidean geometry. And so we've already talked at length about Euclidean geometry and what makes Euclidean geometry so special. We have the elements. It's the big book, which explains all of geometry and a little bit more. It introduced the axiomatic approach to geometry, which has caused mathematicians for the last few thousand years to focus on the idea of creating axiomatic approaches to other things. That led to our axiomatic approach to set theory, which we have since built all of mathematics around. And so this idea of geometry and Euclid's geometry has really taken us quite far. If you don't remember, here are the axioms of Euclid, but we're going to start playing with a few different axioms. In particular, we're going to get rid of the fifth axiom. And so the fifth axiom is known as the parallel postulate. And when we get rid of that, we're able to do some other things. And so non-Euclidean geometry is geometry which uses a different set of axioms. In particular, we get rid of the parallel postulate and replace it with other things. And so typically when you have two parallel lines, they go on forever and stay the same distance apart and never meet. What if they meet? Or what if they don't meet and they get further away? These two cases give us elliptical geometry and hyperbolic geometry. And we're going to see if we can understand what's going on with both of these. To begin with, let's talk about elliptical geometry. What is the geometry on the surface of a sphere? And so elliptical geometry is geometry on a curved surface which has the property that parallel lines will eventually intersect. It can be thought of as geometry on an ellipsoid. More commonly, instead of thinking of an ellipsoid, we think of a sphere. And in that case, we would call it spherical geometry. And so the geometry on the surface of a sphere. In many ways, it is a special case of elliptical geometry and has a number of unique properties. But it's so easy to visualize because we can just think about the Earth and try and visualize what mathematics, what geometry looks like on the surface of the planet. And so let's begin by defining what lines would look like. And so consider 2 points on a sphere. What is the shortest path between the 2 points? Well, the easiest way to picture this is to think of a globe and a piece of string held against it. If you pull the string as tight as you can, what you're going to get is that the shortest path is on what's called a great circle. And so it's a great circle is a circle which spans the full circumference of the sphere. It's not going to be some smaller version. If we were to measure the radius from the center out, this is going to give you a full revolution of the globe. And so a great circle would be the equivalent of the Euclidean line, while the path along the great circle connecting the 2 points would be the line segment. 2 points determine a great circle. And if we were to cut a line across the great circle, we would divide the globe into 2 equal pieces. That's how a great circle works. And so if a great circle is the line, then what would it mean to be parallel in spherical geometry? Well, it wouldn't really make a whole lot of sense. And so consider 2 great circles on the surface of a sphere. How could they be parallel? Well, whenever you have 2 distinct great circles, they're always going to intersect at exactly 2 places. If you want, you could think of them as having a north pole and a south pole where they're going to be crossing. Consider a bouncy ball. If you draw a circle around the main circumference, is it possible to draw a circle around another main circumference without crossing the lines? It's not possible. It's always going to be dividing the sphere into 2 sections, or a great circle is always going to divide it into 2 equal sections. And no matter how else you cut it, those 2 great circles are always going to intersect at different poles. And so because of this, there really isn't such a thing as parallel lines in spherical geometry. And so what do triangles look like then? Well, in Euclidean geometry, we know that the sum of the interior angles of a triangle will always add up to 180. But that's not going to be the truth on the surface of a sphere. If you look at this example over here, we have a triangle which is made up of three lines, the lines being the arcs from a great circle. And in this case, they add up to 90, 180, 270 degrees. And so something weird is going on. And so for a triangle on a sphere, the sum of the interior angles will always be more than 180 degrees. It could be as much as 540 degrees, or at least close to it. Also note that in a triangle, you cannot have two corners in opposite ends of the sphere. And so there is some distinctly different behavior when we start talking about things in terms of a sphere. It's also worth noting when we think about the Earth itself, the shortest distance between 2 points is not necessarily going to be a straight line on a map, because a map is not taking the full curvature of the Earth into consideration. This is where topology comes in. We have to think of a smaller section of the Earth and try and visualize what the behavior is on that particular arc. Hyperbolic geometry is a little bit trickier to visualize. I sometimes think of it as, what does the geometry look like on the surface of a Pringle? Because that's where we see these hyperbolic geometry shapes. And so hyperbolic geometry is a geometry that replaces the parallel postulate with the following. And so for any given line R and a point P not on R, in the plane containing both the line R and point P, there are at least two distinct lines through P that do not intersect R. What this is basically saying is if we look at this image, the line X and the line Y, we are going to say that they are going to go on forever and ever and ever, as is the line R, but X is never going to intersect with R, and Y is also never going to intersect with R. We're going to say that both X and Y are parallel to R. And so this is saying that parallel lines can go through a point and not be unique. And so there can be multiple lines going through a point which are parallel to a given line. In this type of geometry, there will always be more than one line parallel given a point. This complicates things. How do we visualize that? Because this visual that we have here isn't doing it. If we eyeball this, the Y value, or the Y line, it sure looks like it's eventually going to hit. Somehow we have to get this Y line to start curving a bit. And so let's visualize this using art. A hyperbolic plane can be difficult to visualize, and M.C. Escher did one of the best jobs of creating the visual for what a hyperbolic plane would look like. And so he actually did a series of pieces on hyperbolic geometry. We consider the whole circle as the plane, and the white curves would then be lines which are on the plane. And so notice that for any line on the plane, then through any point on the curve, we can construct multiple lines which will never intersect your original line. And so let's look at the line going through this red fish here. And so we have lines going through the red fish here. Well, note over here, we have this line, which is a curve going through these reds. That is going to never intersect with our starting line. But also we have the one involving blue fish over here. This is also going to be a line which is never going to intersect. Both of those lines are going through this particular point. And so now we have two lines which are going through a point and not intersecting with our other line. These would both this blue one and this red one, would be considered parallel because they never intersect. But as you can see, there's a bit of curvature going on. This is what a hyperbolic plane would look like. And this is how we typically would visualize a hyperbolic plane. It's a bit tricky. In this example, this is a different fish example. We can start to see what shapes would look like. And so if we consider each fish as having a length of 1, then we can start to visualize what different shapes look like. In the center region, this would be a square because it has 4, 4 fish of equal length. This one here has 3 fish of equal length as their sides. And so this would be an equilateral triangle. Going out, we can see that we're going to have this is a square and a triangle and a square and a triangle and a square and a triangle. Around any one of these points where all of the lines are meeting, we're going to have 3 triangles and 3 squares meeting. Well, if each triangle has 60 degrees for it to be an equilateral, and each square has 90 degrees, we are going to be, let's see, that'd be 360 plus another 100, or plus another 90. We're going way over the 360 degrees, which would be expected for the distance going around a particular point. And so we start to see some very weird behavior start to pop up. Going back to the original example, this one, every single collection here, every single region is actually a square. And so this is a square with 4 fish. This is a square with 4 fish. This is a square with 4 fish, 4 fish, 4 fish. Every single one of these regions has 4 fish. But notice that we have 6 squares at every convergence of lines. And so we have 1, 2, 3, 4, 5, 6 squares connecting up to this one point. If we assume that each square has a right angle in it, then having 6 90-degree angles would mean that we are way over the 360 degrees that we would be expecting. Either that, or we're saying that a square in this situation is less than 360 degrees as far as the interior angles, which we could visualize that as well. And so this is hyperbolic geometry. It's a little bit weird. There are other geometric structures as well. And so when we think of non-Euclidean geometry, we often focus on those 2 cases, the idea of spherical and hyperbolic geometry. But there are many, many other geometric structures. Again, we're just hitting the tip of the iceberg here. And geometric structures are things which we as humans are really good at understanding and exploring. And so it makes sense that we've explored so many different types of geometry. Let's explore a couple real quick. First one is analytic geometry. This is a big one. And so analytic geometry was developed by Descartes. And it's the study of geometric objects on the Cartesian coordinate system. And so the X and Y axis. In introducing variables, we are able to use algebra to better understand geometric structures. We can then introduce functions to model whatever real-world things we like. Analytic geometry was pivotal because with this, we were then able to develop calculus, which meant that we now had tools to address all of Zeno's paradoxes. And it gave us a new structure to understand geometry. Another one is differential geometry. And so differential geometry studies a great many things. How do we model the motions of a mosquito? We have a tool called a Fermat frame to model such motions. And so we can see the Fermat frame here, and it shows us how we can model something moving in 3 dimensions. More generally, we borrow topological tools of differential manifolds to understand how shapes and structures work in abstract spaces. Differential geometry, for the most part, explores what things look like in 3 and 4 and 5 dimensions when things aren't really working the way you'd expect. Like, what does a square look like on a Mobius strip? Well, we can kind of visualize that, but we might have to be a little weird in some places. Topology and graph theory can also be considered geometric. And so Topology is geometry with a more flexible structure. Of course, we can build and explore structures on topologies, and these include geometric structures. And so sometimes topology is thought of as geometry without all those shapes and whatnot. Graph theory, in some ways, is also a deep dive into the applications of Euclid's first postulate. I can connect 2 points. Thanks, that's all I need. And so graph theory and topology are sometimes grouped together with geometry. Algebraic geometry is another classical approach to geometry. And so algebraic geometry classically focuses on techniques to solve polynomial equations in multiple dimensions, such as the intersection of a plane and a sphere. And so what happens when you take a plane and a sphere and you combine them? Well, we can figure out the types of shapes we get. Typically, we're going to get a circle when we cross a plane and a sphere. What if we took a plane and crossed it with a cone? Well, then we get the conic sections. And so what if we expanded this example to higher dimensions? What if we tried to explore other intersections of things? What types of shapes do we get? Well, that's what algebraic geometry is all about. Complex geometry, similar ideas as regular geometry, but now what if we're dealing with complex numbers? And so what if there are imaginary numbers in play? That's where complex geometry comes in. So mathematical objects are often described using complex components to simplify things. And sometimes we have to do geometry or even calculus involving complex numbers. Calculus on complex numbers is called complex analysis. It's a fun one. There's also discrete geometry. And so discrete geometry is the study of geometric objects as explored through discrete points or amongst a discrete set of shapes. For example, in folding origami, we take a square piece of paper and fold it by connecting certain points together. Well, what types of shapes can we get from a folded piece of paper? As a hint, there are a lot. Quilting, tangrams, and tessellations could be another example in taking a discrete collection of shapes and bringing them together. One common problem in discrete geometry is the number of spheres or M&Ms that can fit in a cube or other region. If you think about M&Ms, how many M&Ms can you fit into a package? Or how many can you fit into a cube? Well, it's a very weird shaped structure, and so trying to understand that can take a little bit of practice. Fractal geometry. Oh, that's a fun one. And so fractal geometry is the study of geometric objects which typically involve some highly detailed self-repetitious structure. These objects are sometimes discrete, sometimes connected. Often they have area but no perimeter, and they exhibit some form of chaotic behavior. This right here is an example of a multibro. I think it's coming from the complex equation z cubed or z to the 6th minus 1. That's a fun one. An often considered application is the idea of measuring a shoreline. And so if you include every bay, inlet, and delta, how would you calculate the length of a coastline? In the case of, let's say, or a bay like the San Francisco Bay or something. Well, how many rivers are there going to it? And where do you cut off where a river starts and where the ocean starts? It can be very tricky to measure that. And also depends on what size instrument you're using to measure. So there's a lot of interesting things that arise in fractal geometry. Another popular one from the last, 20 to 30 years is polygonal modeling. And so the idea for animation, video games, 3D printing, and manufacturing is how can we represent images using polygons? And so here we can see a low poly rendering and a high poly rendering of an individual. As technology has advanced, it has given us a new tool for sculpting, which has applications ranging from art to industry. Those with proficiency in this skill are masters of geometry. Final thoughts? Well, while Euclidean geometry will always be the foundation, over the last few hundred years, we have built on it and developed incredible new geometries. The technology advancements in the last 30 years have created new industries centered around applied geometry, and a variety of new geometric structures have arisen as a result. I mean, there is just so many different types of geometry to explore these days, different shapes that people had never considered. When we're thinking about how a computer is structured, as in the image here, how a processor is formed, it's a geometric object. And it's a geometric object which has trillions of bits, trillions of little on and off switches. And to be able to create something like that, to be able to visualize something like that, let alone create something like that, is astounding. And so modern geometry is definitely a little bit different from Euclidean geometry, but it still has those same foundations. With that, I'll let you get to work exploring where you find non-Euclidean geometries in the real world. Good luck, folks.